I can make this a little bit bigger. Okay. Thank you, sir. Okay. And we talked about where the most reactive metal and the most reactive non-metal were. And we said the most reactive metal is going to be in the bottom left, and the most reactive non-metal is going to be in the top right. Then we started talking about atomic radius. Okay. What happens? What's the trend for atomic radius as I go down a group? This is where we left off the other day. So if I go that way, what happens to the radius of the atom? It gets bigger. Good. Why does it get bigger? Perfect. That's the perfect response. There's more energy levels. Okay. Now let's talk about what happens as we go across a period. Anybody want to take a wild guess? What happens to the size, the radius, as we go across a period? You remember? All right, let's say you don't remember. Let's say you're just sitting out there and you have no idea what the heck's going on. Okay? How can we find out what is happening to the radius as I go across a period? Where would I look? Yes, the reference table. That's a good answer. Where on the reference table? Table S, as in Sally sells seashells by the seashore. Okay, so let's look. Lithium, what is its atomic radius? (130). And then, when we want to find what the trend is that's going across the period, I told you this the other day, we don't look at all the ones in between because there could be some people or some elements in there that are not following the trend. They could go bouncing up and down. We're going to look at the first one, and we're going to look at the last one. So for the last one, I'm going to take fluorine. And what's the radius of fluorine? 60. So now we can see from 130 to 60 what happened to the radius as I went across the period. What's the trend? It decreases. Now, the big question of the day. Big question of the day. Why does it decrease in radius as you go across the period? Let's take a step back. What do all of these guys have in common? All the elements in period 2, what do they all have in common? They have the same number of energy levels. So because they have the same number of energy levels, we would assume, incorrectly, but we would assume that the size would stay the same because lithium has 2 rings and beryllium has 2 rings and fluorine has 2 rings. However, what are we changing as we go from left to right? The number of valence electrons, and there's something else that's also changing. Starts with a P, ends with a roton. Protons, right? And those protons that are inside the nucleus have a positive charge. And the electrons that are in those energy levels have a negative charge, and they're attracted to each other. So you got a positive and you've got a negative that are attracted to each other. Well, those valence electrons that are in the second energy level, if I start adding more protons to the nucleus, those protons are going to be pulling on those electrons in that second energy level, so the second energy level just gets slightly closer to the nucleus because the protons are pulling those electrons, those valence electrons, in just a little itty-bitty bit. Okay? And I believe that's where we left off when we last talked, 2 days ago? Yes, no, maybe? You don't know? You don't remember? Okay. Well, so right now, you should know metallic character, where the most metallic and most non-metallic are. You should know where the most reactive and most reactive nonmetal are. You should also know the trend for the atomic radius. So far, so good, right? I got 2 more trends that we need to tackle. Okay? The next trend that we're going to tackle is called the ionization energy. And I believe this is where we were. Okay? Let's just look at the word ionization. Forget about everything else that's on this page. Just look at the word ionization. What do you think that's referring to? Ions. Okay? And ionization energy is its ability to make an ion. So, energy, when you think about energy, I want you to think of money. Okay? So it's really saying, how much money do we need in order to make an ion? So how much money is needed to remove an electron from that atom? If the atom is really, really, really strong, is it going to take a lot of energy to remove it or a little bit of energy to remove it? If I walk up to a really strong guy and I want the $100 bill that's in his pocket, is it going to be easy for me to get it away from him or hard for me to get it away from him? It's going to be hard because he's really strong. So it's going to take a lot of energy for me to get that $100 bill away from him. If I walk up to a very weak element and I say, give me your money, give me your whatever you have, the electron that you have, it's not going to take me much to get it away from him. Okay? So now, thinking about that information, and we go back to a periodic table. Is this francium holding onto its electron very tightly? Is it strong? Or is it weak? It's weak. Because remember what I said about the electrons being really far away from the nucleus? That francium's electron is really far away. It's in period 7. And it's only got 1 in its outside energy level. So it's going to be very easy to remove an electron from this francium. Let's go to fluorine up here. Okay? Is that fluorine going to be easy or hard to get that electron away from? Hard. Because the electron is very close to the nucleus, and it's got 7 in its valence shell. Okay? So ionization energy is the amount of energy required to remove the electron. It's really the amount of energy required to remove the most loosely bound electron. Okay? And what happens to that ionization energy as you go down a group from here to here? Does it get easier or harder to remove? Mm-hmm. It gets easier to remove. So its ionization energy is going to be lower down here than it is up here. And as I go across a period, what happens to its ionization energy? It gets harder to remove. Okay? So now, the trend, once again, for ionization energy, as I go down, it's going to get lower. It's going to decrease in ionization energy. As I go across, it's going to get higher because it's going to be harder to remove an electron. Now, what about these suckers over here in group 18? What's their ionization energy going to be? Super low or super high? Super high. Why super high? Say it loud and proud. Say it like it is furthest right. And how many valence electrons do they have? 8, except for helium. They have 8. So it's, go ahead, keep going. They don't like to react with anything. So they're not going to lose their electrons very easily at all. So their ionization energy is going to be super-duper high. Because it's going to take a lot of money, a lot of energy, to get an electron away from them. Almost impossible to get electrons away from neon and argon. Here, krypton and xenon, we've seen in the last couple of years that they've started to realize that the electrons are getting a little bit further away, but it's still really high ionization energies. All right, now, again, do you need to memorize this? No siree, Bob, because if you look at table S, on the second or third column over, let's see, what column is it? The fourth column over. See where it says first ionization energy? Everybody should be looking at that table S. I don't have it up on the board here, but you have it in front of you. You see where it says first ionization energy? The word first just means you're removing the first electron. Okay? Let's see what happens to the ionization energy as I go from top to bottom. I'm going to write them up here. Somebody give me the ionization energy of lithium. Say it again. 500? 540? 520. All right, you got to say it like you mean it so I can hear you, because remember, I'm old. My ears don't work as well as young people's ears. What about sodium? 496. See, that worked better. 496. What about potassium? 419. What about rubidium? What do you mean you have no idea? You can't find it? It's number 37. 400? 403. All right, cesium. 55. 376. And finally, francium. 393. Okay. Now, you see how it does a little dipsy doodle here? Where it went down and then came back up? Because trends are not perfect straight lines. We're talking about some of them are going to go up and down. But look what happened from 520 down to 393. What was the trend? It decreased. So the ionization energy decreases as you go down the group. That's the trend. Dylan, you alive? All right, let's go across the period. Lithium we know is 520. What about beryllium? These are nice and easy because they're all in a straight line. So give me some numbers. Beryllium is 900? Yeah. Okay. Boron? 801. Carbon? 1086. Nitrogen? 1402. Oxygen? 1314. Fluorine? 1681. Neon? 2081. Okay. And again, don't look at the little dipsy doodles that are going on in here. Okay, they're going to go up, they're going to go down just a little itty bitty bit. But look at what happens from the first one to the last one. It got harder to remove an electron. Why did it get harder? Because A, the radius is smaller, so those electrons are closer to the nucleus. We looked at radius before. It's also because they have more valence electrons. So the more electrons they have in that valence shell, the less likely they are going to be to give them up. Any questions on ionization energies? Okay. So ionization energy is the amount of energy required to remove an electron. Does everybody have that written down? Let's see. Amount of energy required to remove an electron across a period, the ionization energy is going to get larger, it's going to increase, it's going to be harder to remove the electron from the nonmetals. They want to get electrons. They're going to be easier to remove them from the metals. They want to get rid of those electrons. As you go down a family or a group, it gets easier because the electrons are further away from those positive protons. Any questions on ionization energy trend? All right, the last one is electronegativity. Electronegativity, write this down, is the ability to attract an electron. Now, ionization and electronegativity go hand in hand. A lot of people like to think of them as almost the same thing. They're not exactly the same thing, but they're pretty darn close. Electronegativity is an arbitrary scale from 0 to 4, and what we've done is we've ranked atoms based on how strong they are. So the stronger they are, the higher the ionization energy is going to be. So they kind of work hand in hand. If ionization energy is getting higher, which means it's getting more expensive to get an electron away from it, electronegativity is also getting higher, from 0 to 4. So every single element on the periodic table is ranked, except for the noble gases. Why do we not rank the noble gases? Why do we not care how strong they are?
Because they don't attract electrons.
They don't want to gain or lose electrons, so we don't care. It's like saying, all right, we've got all these people in this room, and you're all going to fight. And Angeli, you're going to be ranked a 4, and Alex, you're going to be ranked a 0.2. Okay? You're really, really strong, and you're really, really weak. I don't know. I just randomly picked it. Okay? Now, everybody fight. You're going to win because you're ranked really strong, and you're going to lose because you're ranked really, really weak. I don't fight. So why would I be ranked at all? I don't have to fight over electrons. I am a noble gas. I have 8 valence electrons. I'm never going to fight. Now, knowing that information, let's go back to our periodic table. Who's the highest electronegativity? Do not look at your table S. Who do you think is going to be the strongest element on that periodic table? And fluorine. And who's going to be the weakest? Say it again. Francium. Good. Now, turn to table S. Fluorine's electronegativity is 4.0. It's the strongest one up there. Francium is 0.6, 0.7? Number 87. 0.7? Yeah. 0.7. See how it's so weak? And that guy's really strong? Look at neon. What do you find for neon?
A line.
A line. That line means it's not ranked at all. Why didn't we rank it? It's not going to fight. Okay? It's not going to fight. It doesn't care what you guys are doing out there because it's already got its 8 valence electrons. Okay. What about lithium? 1.0?
Yes.
Okay. What happens to the electronegativity as you go across a period?
Goes up.
It goes up. Okay, it goes up because you're getting stronger. What happens to the electronegativity as you go down a group? It's decreasing because your electron's getting further away from the nucleus, so if it gets into a fight, it's losing that electron very, very easily. Okay? Do we care what's happening in here? Nope. When you're looking at periodic trends, I want you to look at the first one and the last one. We're going to graph these, and you're going to graph all the ones in the middle, but is that going to matter? Heck to the no. Okay? Any questions on ionization energy or electronegativity? Now, electronegativity we're going to use a lot in the next unit. Okay? Electronegativity is the one that we're going to be looking at. Where do you find it? On table S. You see it's in the 5th column, 1, 2, 3, 4, 5, 5th column over. Okay? Any questions? All right, let me stop this recording. Maybe we stopped the recording. Did I not turn it on? Oh, yeah, I did.